All right, so we've got to go back in time a little bit. It's been an entire week since we last talked about gases. And one of the things that we were kind of building toward with our discussion of gases was the combined gas law. So we talked about the individual pieces of this combined gas law individually. We talked about Boyle's law, the relationship between pressure and volume, how they're inversely related, and how we could, looking at just the top of these fractions, we could equate the pressure and volume at one set of conditions to the pressure on volume at a second set of conditions by multiplying them. We also talked about Charles' law. Charles' law was the relationship between volume and temperature, and the fact that they are directly related. As one goes up, the other one goes up as well. The need for the combined gas law comes mostly from the fact that when I'm looking at a trapped gas, it's usually pretty difficult to hold one of those parameters, volume, temperature, or pressure, completely constant. Yes, there are some circumstances where that is possible. If I have a rigid container, for example, it's not going to expand or contract. If I'm doing work at atmospheric pressure, chances are pretty good that the pressure internally is not going to change. But what about scenarios where that is going to be possible? How do I account for all three of those measured values changing at the same time? And this is where the combined gas law comes in. It's the combination of Boyle and Charles, their two laws together. And what we see out of this law is that exactly the same kinds of things that we talked about before still apply. Temperatures have to be in Kelvin, have to avoid negative or zero kinds of values here for temperature, because they're going to give us either nonsensical values or impossible values for pressure and volume. It's impossible to have a pressure that's negative. It's impossible to have a volume that's negative. And if I divide by zero, any math teacher will tell you that the world will implode. So I have to use the absolute scale. I have to use Kelvin here. In addition, it's about energy. And we know that energy changes are on an absolute kind of scale rather than on a Celsius or a Fahrenheit kind of scale. So let's take a look at an application of this kind of problem. So maybe not quite the scenario of the past couple of days, but not far off. You've got your tires, they are filled up to a warm summer temperature and pressure, 35 psi, 37 degrees Celsius. Your filled volume for your tires is 10 liters. Overnight, temperature and pressure conditions change. See a sudden drop in temperature from 37 degrees to negative 10 degrees. And we measure the tire pressure and find that it's now at 32. Question is, how much has the volume of the tires changed as a result of these other changes? Well, to answer that question, we need to apply the combined gas law. And there's our combined gas law right there. VI/PI over TI is equal to VF/PF over TF. We just have to identify what those parameters are. So we're starting with 35 psi, so that is our initial pressure. 37 degrees Celsius would be our initial temperature. But remember, we have to convert that to Kelvin. So I need to add 273. 37 and 273 give me a total of 310 Kelvin. And my initial volume is 10 liters. my secondary conditions here. I have a new temperature, -10 degrees. So -10 plus 273 would give me 263 Kelvin. And I have a new pressure at 32 PSI. Now, one really important thing to remember when I'm using these gas laws, pressure and volume units do not matter. They can be any unit. I don't need to standardize everything to atmospheres or to torr or to anything else. So long as my pressure units are the same on both sides, I'm okay. So long as my volume units are the same on both sides, I'm okay. The only unit that has to be something specific is the temperature unit. It has to be in Kelvin. So if I plug everything in here, I've got VI or PI is 35 PSI. VI is 10 liters. TI is 310 Kelvin. And on the flip side, I've got 32 PSI for the pressure, unknown for the volume, and 263 Kelvin for the temperature. Now I've got to do some algebra. I need to isolate the V here, so I need to multiply this side by 263 Kelvin and divide by 32 PSI. When I do that, my 32 PSIs cancel, my 263 Kelvins cancel. I'm left with just volume. Whatever I did over here, I've got to do to the opposite side as well. So 263 Kelvin over 32 PSI. And I can see that my numbers don't cancel, but my units do. Kelvin cancels, PSI cancels. The only thing left is liters, which is the unit of volume that I wanted anyway. So now it just becomes a matter of solving. 263 multiplied by 35, multiplied by 10, divide by 32, divide by 310, to two significant figures because I had two here in my initial volume. I'm going to get 9.3 liters. So 9.3 liters would be the volume now of these tires, and so they would appear slightly deflated. Not a terribly large difference between 10 and 9.3, but probably enough to notice that they at least look a little bit saggy or a little bit floppy, depending upon how big they are. Right. Any questions with the combined gas law? Okay, so thus far, everything that we have talked about has largely assumed one thing in common, that we had a trapped gas. We had a fixed amount of gas. But what if we did not have a fixed amount of gas? Well, in that case, we could apply what is known as Avogadro's law. Now, Avogadro's law should make plenty of sense to us, because anyone who's ever blown up a balloon knows that the more air you put into the balloon, the bigger the balloon will get. And that is the essence of Avogadro's law. There is a direct relationship between the volume of gas and the amount of gas in the container. So mathematically speaking, because it's a direct relationship, we again see it given to us as a ratio. But here's what's really interesting about Avogadro's law. Not by the fact that it exists, but by what it means. This particular law applies equally to every kind of gas that is in existence. So this relationship is a common relationship. In fact, it's common enough that if we set some certain parameters, we can actually define how much gas is related to a certain amount of gas. Now, if this sounds a little bit familiar to you, this was the very essence of one of the last labs that we've done, the molar volume of the gas. The relationship in question here invokes standard temperature and pressure, STP. Now, we will find that there are some differing definitions of STP out there. One of the definitions of STP is a common one that was well established over a period of time. It's that STP, standard temperature, is 0 degrees Celsius, 273 Kelvin, and 1 atmosphere of pressure. That is the common factor, STP. That is one of the most commonly used definitions of STP. Not the only one, unfortunately. There's another version of STP where instead of 1 atmosphere, the International Union of Physics and Applied Chemistry said, you know what, 1 atmosphere doesn't work. Reason why it doesn't work is because it's not in standard units. And so they defined the pressure as 1 bar instead of 1 atmosphere. Now, what is 1 bar? 1 bar relates everything back to pascals. So if we talk about pascals and kind of where that kind of goes in, that's the relationship. Now, there is a relationship between the two. 1 atmosphere is equal to 1.01325 bar. So what we can see is that the bar is just slightly lower in pressure than the atmosphere is. What difference does it make in terms of molar volume? It's slight. Now, based on the original definition of STP, with 1 atmosphere being the pressure instead of 1 bar, the molar volume of any gas was 22.4 liters. And that was universal, regardless of type of gas. 22.4 liters was the molar volume. So it didn't matter if you had a really heavy gas like sulfur hexafluoride or a really light gas like helium. Same prospect, same value, same everything. 22.4 liters was equal to 1 mole at those conditions. Under the UPAC system, again, slightly different. 1 mole of gas is 22.7 liters in that scenario. Which is why, if you think back to that lab, you were asked to compare your value to 22,700 milliliters. That 22,700 milliliters was the IUPAC definition of the molar volume. It's also why when you did your conversions, instead of you doing 760 milliliters of mercury or 760 torr, you did 750.7. Same reason. That was the torr equivalent of 1 bar. Now, which one should you use? It depends on your source. I included in your problem sets examples using both. Just to kind of give you completeness of calculation and example. In the macro scale, it doesn't matter that much. In the micro scale, it could be significant enough to notice. Overall, just pay attention. Pay attention to what the book is defining, what the problem is defining as those standard conditions. So the other thing that Avogadro's law does is it does establish for us one other kind of gas law. Now, you could set up a larger version of the ideal gas law where you looked at all 4 of those parameters and how they change. You could set up a new version of the combined gas law this way. Here's a problem though. The number of circumstances where we would actually use this is relatively low. There aren't many occasions where you're going to have a gas that is going to be changing in quantity while the other parameters are changing. Really, the only time you would ever see something like that is during a chemical reaction, or if you had some sort of vessel that had an opening in it, which would kind of negate a lot of this stuff anyway, because the pressure would be changing and the volume would be changing and all that other stuff. What this does establish, though, is that if I look at those 4 parameters next to each other, the fact that they are related to each other means that they all share a common value. They're all equal to the same thing. And that same thing is this value R, the universal gas constant. So if we rearrange and look at this from the standpoint of just how can I define a gas, the ideal gas law comes about as a result. The pressure and the volume of the gas multiplied together are equal to the amount of gas multiplied by the universal gas constant R multiplied by the temperature in Kelvin. Now, there is a little bit of room for maneuverability with the value of R. There are multiple values of R that are possible. If you look at your equation sheets from the experiments, from the tests and quizzes that you've done, haven't had much occasion to use these values of R, but now we're starting to see where they're becoming relevant. And there is an R here for atmospheres, and there's an R here for millimeters of mercury, and there's an R here for torr, and there's an R here for kilopascals. The point of the matter is, R is flexible just as pressure is flexible. So if I have a different unit of pressure, I can use a different unit of R to compensate. They have to match them. So if my pressure is in atmospheres, I need to use the value of R that also uses atmospheres. My pressure is in torr, I need to use the value of R that is also given in torr. And the value for that, just so that you have it, is this. So if you were given a pressure in millimeters of mercury instead of atmospheres, the value would go from 0.0821 to 62.36. Since torr and millimeters of mercury are the same thing, The value for R would be the same for torr as it is for millimeters of mercury. Let's take a look at another example problem. What is the volume of a 0.275 mole sample of hydrogen gas at a pressure of 3.5 atmospheres and a temperature of 37 Celsius? So it can be confusing sometimes when you start getting into all the different kinds of gas law questions that you can be asked in terms of, well, what gas law do I use in what situation? I'll give you a simple rule of thumb. If a question is just asking you to define parameters, like this one is, where I need to know the volume based upon these other measured values, this is where we use the ideal gas law. If I'm describing a gas that is changing, so the pressure is going from this to this, the volume is going from this to this, the temperature is going from this to this, that's where I'm going to use the combined gas law. So combined gas law we use when the gas is changing. The ideal gas law is basically used to describe a gas and basically find kind of the missing parameter. So PV is equal to nRT. My pressure is the 3.5 atmospheres. My volume is unknown. My number of moles is 0.275. My temperature is 37. And I need to turn that into Kelvin. So since I was given a decimal value, I'm going to need to extend my decimal of 273 to 273.15. 37 plus 273.15 gives me 310.15, which I need to round down to just the one decimal place because there was only one decimal place here. So 310.2 Kelvin is my temperature. With all of those values, I can now just plug them in. My pressure is 3.50 atmospheres. My volume is unknown. My moles are 0.275. My value of R, since I am in atmospheres here, is 0.0821 liters times atmospheres over moles times Kelvin. And my temperature is 310.2 Kelvin. From an algebra standpoint, I need to get the volume by itself. So I'm going to need to divide each side by the 3.5 atmospheres. That's going to cross out the 3.5 atmospheres on the left side. Now for unit cancellation on this side, everything kind of comes to the R unit here. I have moles in the denominator. That'll cancel the moles there. Kelvin in the denominator will cancel the Kelvin here. And then I've got atmospheres in this numerator and atmospheres in the denominator here. So they cancel. I'm left with just liters, which is good since this is a volume that we're calculating. 0.275 multiplied by 0.0821 multiplied by 310.2 divided by 3.50 to three significant figures because I've got 3 here, here, and here, but 4 there. It's going to be 2.00 liters. So this is what the ideal gas law is best for. It's best for these situations like this, where we are trying to figure out what we don't know already about a gas. So I knew how much of it we had. I knew the pressure of it. I knew the temperature of it. I could figure out the volume of it from the ideal gas law. Again, that's a different kind of scenario than what we would use the combined gas law for. Combined gas law would be, I know the pressure, volume, and temperature right now. It changes. What don't I know? So that's the big difference between those two. Right? Any questions with the example here? Okay, so a direct application of that ideal gas law is in the combination and determination of density. So density, we know, is mass over volume. Now, with that in mind, it can be a little bit difficult when it comes to gases, trying to figure out how to determine the mass of a gas and how to determine the volume of a gas. But one thing that we do have in common that we can use are moles. From a molar standpoint, I can define a gas by its molar mass. From a molar standpoint, I can also define a gas by its molar volume. And so if I take those two against each other, molar mass divided by molar volume, I would get density. And so that's what this equation is all about right here. So in the numerator, I have the molar mass. And in the denominator here, I have the molar volume. Because we are dealing with gases, it is common to express gas density in terms of grams per liter instead of grams per milliliter. For liquids and solids, we usually go grams per milliliter because they're considerably more dense. But gases, because they are so expansive, we tend to think of them in grams per liter just so that the numbers aren't so small. Now, this last line here about you can substitute those terms into the ideal gas law. I'm going to put a note right there. This is a useful equation, but it can be kind of confusing to actually apply. What I would do instead is if I needed to determine pressure and temperature relationships off of the density of a gas, I'd use the ideal gas law instead. So by using the ideal gas law, I can figure out what the volume should be or what the number of moles should be, and then calculate the pressure or the temperature from there. Let's take a look at another example. What is the density of hydrogen chloride gas at STP? So to answer this question, we can go about it a couple of ways. First of all, we know that density is mass over volume. And if we're looking at it from a specific standpoint, we can look at it as molar mass over molar volume. Now, what does that mean? That means I just need to standardize everything to 1 mole. So 1 mole of HCl, well, its molar mass, I can get off of the periodic table, hydrogen's 1.01, chlorine's 35.45. So 36.46 grams would be the molar mass of HCl. Now, since we are at STP, again, depending upon which definition of STP we use, we'll use the IUPAC version just for clarity because we've used it in other places. We know that this is a 22.7 liter sample at STP. So to find the density, I would just take that mass, 36.46 grams, divide by that volume, 22.7 liters, and I would get 1.61 grams per liter as my density. Be a reasonable way to go about it. Now here's the kicker. What if we weren't at STP? What if we weren't at STP? What would we do instead? Well, I could go back and use that equation, or I could come back to the ideal gas law and say, well, what are my conditions? I need to find volume. Well, if I'm at 1 bar, so just quick conversion, let's turn 1 bar into atmosphere. So 1 divided by 1.01325, I get 0.987. So 0.987 atmospheres times volume is equal to 1 mole times R, 0.0821 liters. Too fast. Liter atmospheres over mole Kelvin, and 273 Kelvin as my temperature. Well, if I solve that for volume, 1 times 0.0821 times 273 divided by 0.987, I'm going to get 22.7 liters, which I can then put into that denominator there and solve it out. So if I was not at STP, so I used STP conditions here, but let's say that it wasn't. Let's say that it was 3 atmospheres and 300 Kelvin. All I would do is just substitute those values in and solve for V. That value of V becomes the denominator of my density calculation. So rather than going through the kind of the process of memorizing that equation here and trying to make sense of this equation to figure out the density, what I can do is I can use the ideal gas law, and it will put me in the right position to answer the question correctly anyway. So for me, I'm about simplicity. I like to keep things simple whenever possible. And so if I have the option of memorizing one equation that does multiple things, I'd rather do that than memorize 2 equations that have specific tasks. Well, you can only use this equation in this way and in this other equation in this other way. The ideal gas law works. So let it work. Any questions with this? All right. Last idea that I want to throw to you today is a relatively simple one. It's the idea that if I have a mixture of gases, each one of those gases will exhibit its own pressure. The pressure that we are discussing is something called the partial pressure. And the partial pressure of a gas is simply the individual pressure that it exhibits in the overall sample. So if I was going to take the total pressure of the gases in this room, I would have oxygen and nitrogen and carbon dioxide and a whole bunch of other gases. Each one of those gases has their own individual pressure. If I add all of those pressures together, I would get atmospheric pressure, which I would be able to measure with a barometer. Now, if I wanted to know the individual pressure, I need a little bit more information. That little bit of information is something called the mole fraction, which basically just tells you what percentage of the total gas is the gas that I'm interested in. And so if I take that percentage of gas that I'm interested in and multiply it by the overall pressure, I can get the partial pressure of the individual gas. So it's a nice thing. It works kind of both directions. And I'll leave it at that. So on your way out, make sure that you touch on this question here. And then on Wednesday, we'll do a little bit more with Dalton's law. We'll also touch on Brand's law of diffusion, and we'll get into gas phase stoichiometry, as well as finishing it out by talking about what happens when a gas doesn't obey the kinetic molecular theory. How do we adjust for that? That'll be it. Have a good day.